So hi everyone. In this lecture, we were actually analyzing the pulse response of integrators and differentiators, but we were starting with ideal integrators and ideal differentiators, and then we said we will slowly start adding non-idealities. We'll add finite gain of the op amp, finite UGB of the op amp, and then saturation limits for the op amp, and then do the analysis of pulse response of these circuits. But before we go there, I wanted to do a quick review of frequency response or sinusoidal response of integrators and differentiators. So I want you guys to be at a position where you are very comfortable with analyzing basic op-amp based integrators and differentiators with finite gain and UGB at a system level. Okay, you should be comfortable to analyze them and be able to draw Bode plots for these transfer functions. So let's quickly, as an exercise, start with the first problem. I think you can very easily say what is the transfer function for this circuit. If I were to ask you V naught by Vi of S, what is the transfer function? So that's a simple circuit, right? It's a very, and at this point, it's a inverting integrator. And then it is -1, so it is a non-inverting integrator. So there is nothing very confusing here. If I ask you, what is the current that this first op amp is supplying, what will be your answer? What is the current that the first op amp is supplying? It will be a frequency dependent current. So you have to keep in mind it's a frequency dependent current. What will be that current? See, picture is this way. The op amp is supplying current. There are two paths for the current. One is the current that flows through the cap and the input port. Then there is another current which is flowing through the next stages op amp's input. So what will be this current through the capacitor? What is that current? That is nothing but Vi by R. That's this current. And the current flowing through this input of the second resistor, or input of the second inverting amplifier circuit, is what? V naught by R. So you have, so this current is Vi by R, but the directions are different. Vi by R is entering, V naught by R is leaving. Okay, so you'll have V naught by R. So if I calculate, your I naught will be equal to V naught by R minus Vi by R. And what is V naught? V naught is 1 by SRC times, let's write it in terms of Laplacian variables. So then V naught is simply minus 1 by SRC times Vi by R minus Vi by R, capital Vi by R. So if I compute, the total current that you are supplying is simply Vi of S with a minus sign by R into 1 plus 1 by SRC. This is the total current that the op amp is supplying. Okay, just to keep, I just want to get your analysis skills good so that we will be deriving more complex transfer functions very soon. So I'm just doing these exercise problems to build your skills. That's it. Now this problem, the second one. Can you guys analyze and tell me what will be the total transfer function to the output? See, anytime you have look at this circuit. There is a negative, there is a loop here. Anytime you have some feedback, you have to first ensure that is it positive or negative feedback. Is this feedback positive or negative? If I traverse, there are two op amps in feedback. What kind of a feedback do you think it is? Do a quick test. Break at this point. If you apply a small change, and then let's return back to the same point. You apply a small change delta V, this node will increase. This cap and a resistor, it's a passive circuit. So therefore, this node will increase. Yes. So which will lead the output node to go lower. It will decrease. So an increase in this node led to a decrease in the same node. So it's a negative feedback. Okay, so it's a negative feedback. So the moment you know it's negative feedback, you can immediately apply this result. V plus will be equal to V minus. So this node will be at ground, virtual ground. So if this node is at virtual ground, now you can quickly analyze and tell me what is the output of the circuit. Same? Did you guys get the same transfer function? It's the same, right? So if let's assume VO1 is this node, the same VO1 appears at this capacitor's input as well. Yes. So it's the same circuit, and you'll get a transfer function of VO by VI of S is 1 by SRC. What is the difference? If I ask you to calculate what is the current that this op amp is supplying, I naught of S, what will be your answer? What is the current that this op amp is supplying? This op amp, oh, only V naught by R, right? Only V naught by R. So it's VO by R, there is no current in this direction because this input current is 0, op amp's input current. It is supplying a current of V naught 1 by R, which is nothing but minus 1 by SRC times VI by R, V capital I by R, and capital VI by R. So this is your current. It's a frequency dependent current, and that's being supplied by this op amp. The input current, the current that flows through the capacitor, actually is supplied by this voltage follower. This voltage follower will supply that current. Okay, that's the difference between these two circuits. Yeah. Next, this one is a little bit complicated, but you should be able to solve it. Use again basic rules. Whenever you are given a circuit like this, see that there is a feedback, right? The output of this guy is being fed back at the input of the first op amp. So check what kind of a feedback is this first. Step one, once you are given this, immediately check what kind of a feedback it is. Break the loop at some point and check if you increase this node, what happens? What kind of a feedback is this? What kind of, yeah. So one of you got it right. It's a negative feedback. So if I increase this node decreases, and it's a passive circuit. C and R is just a capacitor and resistor is just a passive circuit. So if I increase this node will also increase. So here this node is decreasing. So this non-inverting terminal will decrease. So this node voltage will decrease. So it is in negative feedback. So that's not a problem. So the moment that tells you that the second op amp is in negative feedback. The first op amp is in negative feedback. This is anyways in negative feedback because this output of this is fed back to locally, it's fed back to its own inverting terminal. So this op amp is anyways in negative feedback. So both the op amps, I can use this condition V plus equals V minus. So this will be at 0, this will be at 0, this will be at 0, and this will also be at 0. Now, can you quickly do the analysis and tell me what do you get out of this? So this, let me, to remove any confusion, let me call this VR1, R1. Okay, I was calling R and R previously also, just to separate, this is a different resistor compared to this one. What is the transfer function? See, I'm interested in this node. This is the node I'm interested in. Let's assume this node is V naught. This node voltage will be minus V naught. It's an inverting amplifier. Now, at this node, if you see, right, the sum of these two currents, this node voltage is known. You know the node voltage, but the sum of these two currents is 0 because no current goes into the op amp. Use that condition, and you can quickly see that the output voltage, you can find it. Or if you don't want to do that, then you can simply find the current VI by R. It flows through this capacitor and then into this op amp. Okay, VI by R current flows through this capacitor into this op amp, and the voltage developed across the capacitor will be in this direction. That will be what? VI by SRC. Okay, but remember, that is also equal to V naught. That's what this circuit is doing. Previously, if you recall, in an inverting integrator, the voltage across the capacitor at this node was normally at V naught. Now I have made it minus V naught. Okay, so what can you say? You can simply say V naught will simply be equal to VI by SRC. So it's a non-inverting integrator. If you don't want to do that, it's straightforward KCL and will give you the answer. You can apply KCL at this node. At this node, the current due to the current flowing through the resistor is VI minus 0 by R. And the current flowing from the capacitor into this node, that will be minus V naught minus 0. So that will be minus V naught by SC into SC equals 0. So you equate this, V naught by VI will be 1 by SRC. So what you get here is a non-inverting integrator using a slightly different configuration. Okay. The op amps, the current that input is drawing, the current that flows to the resistor comes from the second op amp. That's the path for the current. First op amp only provides current for this guy through the resistor R1. Second op amp has to supply two currents. One is the current through this from this op amp and the current through the input as well. So all three circuits, if you see, right, this op amp's output was not supplying VI by R. First op amp's output is not supplying this current VI by R. There is another op amp which is supplying. And I just showed you guys the transfer function is 1 by SRC for this circuit. Okay, so just to quickly show you guys, see, previously, if you take a non-inverting integrator, the voltage across the capacitor was what? V naught. If from output node, this voltage is at 0, it was V naught. I just flipped this voltage, that's it. I just, instead of making this node we just cut this node off and ensured this is minus V naught. Minus V naught, sorry. Minus V naught. So instead of plus V naught, now we made this other terminal voltage to be minus V naught. And so we got one inversion. That's how we got this inversion in the integration operation. Okay. So that's a quick analysis of three different circuits. Now we'll look at how to plot the frequency response graphs of integrator circuits. So let's start with a simple inverting integrator. The transfer function of an inverting integrator with an ideal op amp. An ideal op amp, open loop gain is infinity. Gain bandwidth product is infinity. We denoted the symbol gain bandwidth product as omega u. Okay, then that is infinity. No poles in the op amp. DC gain is also, that's an ideal op amp. If you use that, this is an inverting integrator with a transfer function of minus 1 by SRC. And if you plot the frequency response, now this is with respect to omega in radians per second. If you plot the frequency response, it will just be a linearly decreasing function with a slope of, what will be the slope? It's a first order, it's decreasing. If I asked you in terms of decibels per decade, what will be this? Minus 20 decibels per decade. Okay, for a single pole, it will be minus 20 decibels per decade. So if I have a transfer function like this, 1 by SRC whole power, capital N, and if I plot its Bode plot, what will be the slope with which the function will decrease? Minus 20n, that's it. Okay, so that's the advantage of log functions. Anything is anything that's raised to the power will become linear in the log scale. So it will be minus 20n decibels per decade. What is of interest to us whenever you look at a graph like this is this point. That's the unity gain frequency. The frequency at which the integrators gain becomes equal to unity. Right? At that point, until then, you feed any sinusoid. The output will also be a sinusoid, assuming the sinusoid has DC voltage, zero DC volts, zero DC voltage across it, zero DC average. Output will also be a sinusoid. Okay, we'll come to what is the phase, but it will be a sinusoid with an amplitude greater than the input amplitude. But any frequency greater than 1 by RC, 1 by RC radians per second, the amplitudes will slowly decrease. This is sinusoidal response. At omega equal to 1 by RC, the magnitude of this function is 1, or on a dB scale, it will be 0 decibels. Right? What I'm plotting is 20 log of mod of 1 by omega RC. This is what I'm plotting. That's the magnitude response, which is what we are plotting. For a differentiator, okay, let me finish one more point. Yeah, sorry. So anytime you are plotting frequency response, there are two things of interest. One is magnitude, because frequency response, if you see it, h of omega is a complex number, which has both magnitude and phase. So it will have mod of h of j omega, okay, or let me write j omega, e power j angle of h of j omega. This we normally call it as j phi of omega. Okay, so if you know magnitude response and phase response, then you can uniquely determine what the transfer function of the system is. So if you know what the magnitude response and the phase response is, sorry, you can't uniquely say, you can say roughly what the transfer function is going to look like. Okay, yeah. So now we have drawn the magnitude response. Let's look at the phase response. The transfer function is minus 1 by j omega RC. There is a minus sign already. A minus sign corresponds to a phase shift of minus pi or minus 180 degrees. See, whenever I put a term minus, normally I indicate a phase delay, a phase lag. Okay, minus just indicates a phase lag. So if you feed a sine wave, it will be shifted in the forward direction. That's what phase lag means. That's what we expect in causal systems. So once you apply an input, then you get an output. So there is a phase lag between input and output. The minus sign will give me minus pi. What will be the phase shift due to 1 by j? 1 by j. Due to j, it is j pi by 2. It will be minus pi by 2. So it will be minus pi by 2. So the overall phase shift will be minus 3 pi by 2 or minus 270 degrees. So an integrator, no matter what the frequency of the signal is, you feed any sinusoid as an input to this integrator, the output sinusoid will be phase shifted by minus 270 degrees. So generally, if you feed sine of omega naught t, output frequency will remain the same. But this, I can say minus 270 degrees is also equal to plus 90 degrees. If you feed sinusoid, what should I get at the output? Minus 270, you can treat it as plus 90. I'm feeding a sinusoid, sine signal, sine of omega naught t. What do you expect at the output? Forget about its amplitude. What kind of a waveform will you get at the output? Yeah, sinusoid with 90-degree phase shift. What is a sinusoid with a 90-degree phase shift? A cosine. It's a cos waveform. So if you feed a sine, you will get cos. So just keep that in mind. The total phase shift of an integrator is minus 270 degrees. So, or mathematically, it's also equivalent to plus 90 degrees. But I don't want to write plus 90 degrees because it gives you an impression that there is a phase lead. Okay, if you feed a sinusoid, there is a phase lead. So I don't want to look at it that way. Instead, look at it as a phase shift of minus 270 degrees. If I were to ask you, what is, if the integrator was a non-inverting integrator, what will be the phase response? A non-inverting integrator. What will be the phase response for this? Minus 5, that's it, minus 90 degrees. That's it. So I'm just giving you an understanding. A non-inverting integrator gives you a net phase shift of minus 90 degrees. Okay. So inverting integrator means you're adding another 180 degrees to it. So that's why you're getting minus 3 pi by 2 or minus 270. So sometimes I've seen it represented as plus 90, but that doesn't make sense. Write it more in terms of minus 3 pi by 2. Okay. Let's come back to this result. The second one is an ideal differentiator, inverting differentiator, minus SRC. If you see, right, this transfer function will be minus j omega RC. The magnitude response will be 20 log of omega RC. Now, you know, log of 0 is minus infinity. See, log of 0 can be seen as 10 power minus infinity, so it is minus infinity. And this function will linearly increase with omega. Okay, it'll be a linearly increase with log of omega. So this function can be written as 20 log of omega plus 20 log of RC. Okay, so if you see this term has a slope of 20 decibels per decade. So if you change omega by 10, this is log to base 10, it will increase by 10. So for every decade change in frequency, your amplitude will increase by 20 decibels. So this will linearly increase on a log scale at the rate of plus 20 decibels per decade. And the point where its gain becomes equal to 1 is the derivative frequency, which will be 1 by RC. That's the point where your gain becomes equal to 1. And if you see, both these guys have a very similar point. I mean, they both go to unity at the same point. Differentiator and ideal differentiator and ideal integrator with the same time constants have a same, they both go to unity gain at the same frequency. So differentiator will look like this. That's it. It'll be the same graph, but it'll, at this point, it'll go to 1. But at high frequencies, it'll do the opposite. It'll keep decreasing. Now, if I were to compute the phase response, this is what? Minus SRC. Sorry, minus SRC. That is minus j omega RC. What is the phase response? It'll just be minus pi by 2. Just minus 90 degrees. So if you feed an input sinusoid, output will be, what kind of an output should I expect? If I feed a waveform of this type, sine omega naught t, what kind of an output can I expect? Forget about the amplitude. I should expect cos of omega naught t. That's it. So this property is called quadrature signal generation, meaning to both the differentiator or integrator, if I feed a cosine signal, I will get a sine wave as an output. If I feed a sine wave signal, I will get a cosine waveform as an output. So I've shown here the waveform of the input and output waveforms of an integrator. The way in which we are going to work this one is that we are choosing the input frequency of the sinusoid to be equal to 1 by RC. If I choose the input frequency to be equal to 1 by RC, what will be the amplitude of the sinusoid at the output? If this V peak to peak is V peak, what will be the amplitude of the sinusoid at the output, the peak to peak at the output? Same peak, right? Because why is this peak same? The frequency is 1 by RC. And what is the magnitude response? What is the value of the magnitude response at 1 by RC? 1. The gain of this integrator is just 1. Therefore, the amplitude will exactly be the same. Now, we know what is integral of sine. Integral of sine x is minus cos x, right? Plus some constant. Let's assume the constant of integration is 0 right now. Integral of sine x is minus cos x. So how do you verify this? Just differentiate cosine once. That will be minus sine x. So minus of minus is plus. So if you differentiate it, you should get your input back. If you integrate a sinusoid, you should get minus cos x. But since it's an inverting integrator, you are doing minus of integral of sine x. you should get plus cos x. Okay, so that's what will happen. You take a sinusoidal waveform. This is your sinusoidal waveform, and you're going to shift it by 270 degrees. Okay, and you'll see a waveform that should look like this. Or I can think of it like this. This one here is 90. Okay, or I can shift this waveform by plus 90. Am I making some mistake here? See, the waveform should look like this. For an inverting integrator, the output is plus cos x. So that will be sine of omega naught t plus pi by 2. Is that right? So sine of omega naught plus pi by 2 will give me, this is in the second quadrant, right? So this should be pi by 2 plus omega. Will it be in the, or I can, oh, this will come in the third, is it? So I can write it as omega t minus 3 pi by 2. Shift the signal, that's what. So that's what I did. So if I shift the signal right, I will get, oh, you're right. So I can shift the signal right, or I can shift the signal left by, oh, I mean, I'm really sorry. It's a very straightforward analysis. I'm really sorry. I just got confused with the number sequence. Okay. So you're right. You guys are right. So if I have a sine wave here, right, this is the origin. I can either shift this waveform by 90 degrees in this direction, or I can shift this waveform by 270 degrees in this direction. Both are same because it's a sinusoid. Both are same. So if I shift this waveform by 90 degrees on this side, what do I get? I get the sine wave shifted here. I get a cosine waveform as it is. You're right. Okay, the peaks will not match. There will be 90-degree phase shift. Yeah. So if I shift the waveform by 90 degrees on this side, on the left, I will get this peak. This peak will shift to origin. So that's a cosine waveform. Okay. Okay. I'm sorry. I think I wasted my time there, but that's what you get. So you'll get a cosine waveform, which is predicted. Okay. Yeah. So now if you see, right, I'm feeding a sinusoid. I'm getting a cosine waveform at the output. So these two signals are called quadrature signal because they both are at 90 degrees to each other. Okay. The frequency is same, but phase is 90 degrees off. And they are very useful in communication systems. So you must have heard of words like quadrature amplitude modulation, okay, where you will modulate bit data streams on two quadrature carriers which are 90 degrees phase shift off. I'm just giving a very crude example. The systems that we use today, they operate at much higher frequencies. So an op-amp circuit may not work, but the idea is somewhat like that. You can think of it like that. Okay. So if I feed it a sinusoid, I'm going to get a cosine waveform. And we will see later, at a later time in the course, we will see that there are such circuits called quadrature oscillators. We will build some oscillator circuits where we exploit this very principle. We exploit this very simple principle where we feed sine and get cosine at the output. That's it. Okay. So, yeah, the next step, let me just